Hello, and welcome to the asynchronous session for Calculus of Integrals on March 31st. For this session, we are going to talk about double integrals. That is, we are going to continue our discussion, and specifically, we are going to talk about when double integrals are not bounded by rectangular regions, and when switching the order of a double integral can make a difference in the difficulty level of it. Before beginning, it is a good idea to attempt these three tasks on the intro slide on your own. When you are attempting these tasks, pause the recording, complete them, and then turn the recording on as I will explain the answers. Now that you've had a chance to complete the intro tasks, let's talk about them. So, a double integral relates to the graph of a function of two variables in that if we take the double integral of a function of two variables, we get the volume underneath the surface formed by that function. Next, for the second one, to calculate the integral from 1 to 3, integral 0 to 5, x cubed y minus x dy dx, we start out by taking an antiderivative with respect to y. That becomes 1/2 x cubed y squared minus xy, and we evaluate that from y equals 0 to y equals 5. Doing so results in the integral from 1 to 3, 25 over 2 x cubed minus 5x dx, and from there is just a standard integral. And it becomes 25 over 8 x to the fourth minus 5 over 2x squared, evaluated from x equals 1 to x equals 3, and then we plug in the limits. For problem 3, it is best to do a u substitution. In this case, our inner function is 5 times sine of x, and conveniently, the derivative of 5 times sine of x is 5 times cosine of x dx, meaning if we set u equal to 5 sine of x, du is equal to 5 cosine of x dx. We can then convert the limits to be in terms of u, which is a step that we have to do. So if we plug in negative pi over 2 for x into the equation for u, we get 5 times sine of negative pi over 2, which is negative 5. If we plug in pi over 2 for x into the equation for u, 5 times sine of pi over 2 is equal to 5, which then converts the integral to the integral from negative 5 to 5 of e to the u du. Noting that the antiderivative of e to the u is just e to the u, this results in e to the u evaluated from u equals negative 5 to u equals 5. Plugging in those limits and subtracting gives us a final answer of e to the fifth minus e to the negative fifth. A part of double integrals that we did not encounter with single integrals is with double integrals we can actually switch the order of which variable we integrate with respect to first. So in this case, if we are integrating, we're taking the double integral over a rectangular region of y times e to the xy dA, where the rectangular region is from 1 to 4 in x and from negative 3 to 5 in y. We have the option of integrating with respect to x first or y first. In some cases, it doesn't make much of a difference. However, in other cases, by switching the order of integration, it can turn a simple integral into a complicated integral or vice versa. So let's explore what happens with each order and see the importance of choosing the correct order of integration for a double integral. So we're going to talk about integrating with respect to x first and integrating with respect to y first. By the way, the variable we integrate with respect to first should go on the inside. So integrating with respect to x first would mean placing the limits for x, 1 to 4, on the inside integral and dx on the inside. This results in the integral from negative 3 to 5, integral 1 to 4 of y e to the xy dx dy. Think back to the intro problems because you may notice a similarity between this problem and one of the intro problems. If you notice, inside of the exponent for e, we have more than just a variable. So, similar to the intro problem, we can do a u substitution for this case. So, in this case, the inner function is x times y, which, if we take the derivative with respect to x, gives du is equal to y times dx. Also similar to the intro problem, we have to convert the limits as well. If we plug in the lower limit, which is x equals 1, that gives us a lower limit of y. If we plug in the upper limit of x equals 4, then that gives us an upper limit of 4 times y. Because again, we are just plugging in those numbers for x so that they are limits in terms of u. Also, by making the substitution where we used u equals x times y and du, which is the derivative with respect to x, was y times dx, the integral now becomes e to the u du dy. This is an identical integral to the intro problem in the sense that the antiderivative e to the u is just e to the u. And then from there, we're going to plug in the limits with respect to u. So we have lower limit of u equals y and an upper limit of u equals 4y. This now results in the integral from -3 to 5 e to the 4y minus e to the y dy. Next of all, we integrate with respect to y, as this is now just a typical integral from earlier in the course. Integrate with respect to y, which, by the way, the first part of this, you might want to do a u substitution. You don't necessarily have to if you have the process very much in hand. But either way, integrating with respect to y gives us 1/4 e to the 4y minus e to the y evaluated from y equals -3 to y equals 5. From there, all we have to do is plug in and subtract. Now, let's consider what happens if we integrate with respect to y first, meaning that dy will be in the inside and the limits for y will be on the inner integral. Setting it up this way gives the integral from 1 to 4, integral 3 to 5, y times e to the xy dy dx. Again, we still have an inner function with respect to e, although something you might want to try. See what happens if you try a u substitution. Noting that this time du you would have to take a derivative in terms of y. If you try to take a u substitution, you end up running into issues and it doesn't work. Instead, the only way that this can be solved is integration by parts. As again, we are considering x to be a number, so this is really similar to an integral like y times e to the 3y dy, which, if you remember, required integration by parts and required a number of steps. For that reason, this is a case where we would choose to integrate with respect to x first, as it is a much simpler process. I realize it's not short, however, sorry, you are in upper level math. Short doesn't happen very often. So, anyway, this is one of the situations where integrating with respect to one variable first makes a significant difference. In transition, I would like you to attempt each of the problems below. At this time, please pause the recording, make an attempt. Once you have attempted these, you can resume the recording and check your work. So, now that you've had a chance to attempt these, let's go through them. So, for the first one, we would start out by taking an antiderivative with respect to y, which gives the integral from 0 to 1 of y evaluated from y equals x to y equals square root x. Because we know that the antiderivative of 1 times dy is just y. Plugging in gives the integral from 0 to 1 of square root x minus x. then integrating that with respect to x gives 2/3 x to the 3/2 minus 1/2 x squared, which if you then plug in 1 and 0 and subtract, you get 1/6. Next, for finding the area between two curves, we take the integral of the curve that's on the top minus the curve that's on the bottom. In this case, the curve that's on the top is y equals the square root of 5x minus 4, and the curve that's on the bottom is y equals x. This results in the integral from 1 to 4 of the square root of 5x minus 4 minus x dx. Something I want you to note is the similarity between what we have here and what we have there. Because, as it turns out, this integral right here is actually finding the area between the curves x and square root x from 0 to 1. So this is a tie-in between double integrals and single integrals. And that is, if we take the double integral of 1, then we are just finding that area in the xy plane. Either way, continuing on with the second problem, plugging this into a graphing calculator or doing it manually gives a is equal to 0.9. The result of that last slide indicates one application of double integrals, and that is if you take the double integral of 1, it gives the area of that region on the xy plane. So the two scenarios, as is similar to what we did earlier in the course, we calculated areas between curves. If you have an area that is defined as y between functions of x and x values, then you can write this as the integral from the numbers that bound x, then the functions that bound y of 1 times dy dx. Conversely, if you have a region that is bounded by functions of y, then you can define this as the integral for the numbers that bound y of the integral of the functions of y that bound x of 1 times dx times dy. So now we are going to apply this concept. We are not going to go too much in depth, as this is meant just to be a demonstration so that if you come across this in a science or engineering application, you know what to do. So we will set up double integrals to calculate the area for each of these situations. On the first one, we want to find the area between the curves y equals negative x squared plus 9 and y equals x squared minus 9. On the interval, negative 3 is less than or equal to x is less than or equal to 3. A key point is that for double integrals, the outermost integral must have numeric limits. That means our outer integral will be the integral from negative 3 to 3. Our inner integral will be from x squared minus 9 to negative x squared plus 9. As a general rule, find which curve is on the top with respect to positive y or positive x, and put that as the upper limit. Please note, if you flip it around, the only difference is the integral will be negative, which will be a clear indication. So either way, our answer here is the integral from negative 3 to 3, integral x squared minus 9 to negative x squared plus 9 of 1 times dy times dx. Noting that when we are finding the area using a double integral, the function inside will always be 1. For the next one, instead of y being bounded by functions of x, we have x being bounded by a function of y. So the key point here is that the outer integral must have numbers. So with that in mind, our outer integral would be the integral from negative 1 to 3. The inner integral would be from y squared minus 2y plus 2 to 5. Because we are calculating area, the function inside the integral is 1, Now we are integrating with respect to x first, so it is dx on the inside and then dy on the outside. This is the general idea of using double integrals to calculate area.